Okay, folks, so now we're going to talk about something called multiplicity of zeros. Now, multiplicity is a concept you've heard of, like multiples, right? Like multiples of 9, 18, 27, so on. Well, how many times we're multiplying, right? By 2, by 3, and so on. So multiplicity of zeros is going to be something very specific. Multiplicity we're going to define in terms of how many times something is repeated. Now, so you can have multiplicity 1 zeros, which means they're not repeated at all. Multiplicity 2, they repeated twice, and so on. You've seen this before, you just may not have recognized it. So, factored form tells you a lot about a polynomial. Meaning, if I gave you a polynomial such that it was of the form y equals x plus 2 times x minus 3, you should recognize that as a quadratic, and that there are two roots. One root, or 0, is -2, and the other root, or 0, is +3. Versus another quadratic like x plus 4 quantity squared, which is still, right, a quadratic, because in reality that's what this is a shortcut for. It means that it only has one 0, -4, but it's being repeated twice. So we'd say that each of these zeros, they're only happening once. These zeros have a multiplicity of 1. Both of these have a multiplicity of 1. And this 0 has a multiplicity of 2. Now, one way to think about it also is, if this is the same as raising this to the first power, and this is raising this first, which means that the exponent or power that you're raising a particular 0 is also the multiplicity. Okay? Now, you have seen multiplicity 3 zeros. It's x minus 5. That would be this. So this is x minus 5 cubed, and we'll talk about what that actually looks like here in just a sec. But we have these. We're going to take this x minus 5 cubed. That would have a multiplicity of 3. That is, it's being repeated 3 times. Now, you can kind of take this to the extreme, and you could have x minus 2, and it could be squared times x, let's say, to the 4th, times x minus 3 times x plus 4 times x minus 7, let's say, cubed, right? This means you're looking at one heck of a polynomial. In fact, a polynomial with a bunch of zeros. It's got one, remember, this x to the 4th is really the same as saying x minus 0 to the 4th, right? And there's a 3, and there's a -4, and there's a 7. But they all have different multiplicities. They're being repeated a different number of times. This one's twice, 4 times. Both of these are 1, and this is 3. The reason that's kind of important is because we can figure out what the degree of the polynomial is. Now, if we think about this, one of these and one of these are multiplied, that's degree 2, quadratic. This means this, which is also degree 2. What's this degree? Well, that's x minus 5 times x minus 5 times x minus 5. It's degree 3. In other words, the multiplicities taken together tell us the degree, which will be very important when we're considering things like end behavior. Remember, odd degree versus even degree. So in this particular case, we could take all these degrees and we could add them together. Now, the reason this works is you're going to have 2 x's being multiplied here, 4 x's being multiplied here, total of 6 x's so far. Another x gets multiplied in, that's 7. Another multiple, that's 8. And as a matter of fact, if we add all these up, add all these degrees up of each of the zeros, let's see if I can do this right. 6, 7, 8, 9, 10. This is an 11th degree polynomial. Now, that does mean it's odd, and that's where it becomes important. We'll take a look at an example. You can see what I'm talking about. But first, we're going to talk about what the heck these things look like. So let's take our examples, and actually we can just kind of, I think we can just cut and paste. Let's see. Copy and paste. So what I'm going to do is sketch what these are and see if we can figure out any sort of pattern. Let's space these out first, okay? So what we're going to do first is draw some axes, right? So this is going to graph a certain way, this is going to graph a certain way, and this is going to graph a certain way. All right, you can probably predict what most of these are going to graph like, to be quite honest with you. At -2 and at +3, and we're assuming that's just a +1, right? So it's going to open up. That means that it's going to go like that. 2 roots, bada bing, bada boom. This has been shifted 4 units to the left, so it's going to hit at -4. That's where the 0 is. Because this is positive, it's just going to hit the axis and go up like that, right? This is a cubic model. Remember, cubic models generally look like this, right? And what's going to happen? Well, it's going to cross at a +5 because that's where the root is. So just to save myself a little bit of grief, this is going to cross right like that, okay? Now, do you see a difference between these multiplicities? Remember, these were multiplicity 1, multiplicity 1 zeros, multiplicity 2 zeros, and multiplicity 3 zeros. These seem to cross through the axis, and they just cross through the axis. Pretty straightforward, right? Multiplicity 2. Does that cross through the axis? No. Does it touch the axis? Yes. So I would say it kind of bounces, if you will, right? And last but not least is multiplicity 3. Well, these are both odd, right? Does this cross through? Yes. Does this cross through? Yes. But this crosses through in a different way. This crosses straight through. This kind of takes a little pause there, right? Now, it turns out this pause, so when you're looking at it, and I know I've talked about this, if you wanted to construct a cubic, you could take kind of like this quadratic and another quadratic, right? And kind of, so if you're looking at this, we got a quadratic opening up, and we got a quadratic opening down, and we could kind of delete portions of those, and we end up with our cubic such that this point right here is where it changes from opening up to opening down, or vice versa, depending which way you're going, right? So we'd say that this is a point of inflection where what's called the concavity changes. Concavity is like open up or open down. So we can say something's concave up or concave down, right? And that point right there where it changes is called a point of inflection. So to sum up, we've got multiplicity 1 roots, which seem to cross and just cross straight through. Multiplicity 2 roots, which, well, seem to touch, that is bounce, right? And multiplicity 3, which cross, but they kind of do this kind of squiggle. So in words, multiplicity 1 zeros do indeed cross straight through the axis, whereas multiplicity 2 bounce off the axis. Multiplicity 3 cross the x-axis with a squiggle, with actually an inflection point where they change concavity, right? So let's take a look at an example of how we can use this. Meaning, what if someone like me presented you with this equation? First off, hopefully you see that this is a root. Remember, this is the same as saying x minus 0 to the 4th, right? There's 1 root there, 2, 3, 4. There are a total of 5 roots. So we know that this graph, if we were to graph it, which we're going to do, it looks like a mess, but it's not as bad as you think, is going to hit at 0, right? It's going to have a root at -3. How do I know? Because that's a root at -3. And it's going to have a root at 2, positive 2. It's going to have another root at positive 5, and it's going to have yet another root at positive 4. Now, what's true about these? So this root right here has a multiplicity of 4. This root here is multiplicity 2. Both of these together are multiplicity 1, and this is another multiplicity 2, right? So what does that mean? Well, it means we know that at this point now, 4 is an even number, so it's going to bounce. 2, it's going to bounce. Multiplicity 1 is going to cross straight through, and here it's going to bounce. Now here's the problem. Where does the graph start? It could start up here, and then it would come down, and at -3 it would bounce, and then it would bounce again, and so on, right? Or it could start down here, right? So in other words, the end behavior could be that it starts here or it starts here. So how do we tell the difference? Well, what we do is we find the degree of the polynomial, which is actually the sum of the multiplicities. So 4 plus 2. These are both 1, so 2 1s, plus another 2. So 4, 5, 6, 7, 8. This is degree 10, which is indeed even, right? Now, if it's even, that means it's either opening up for the end behavior or it's opening down. How do we tell the difference, right? We know that the end behavior is going to be x goes to positive or negative infinity. It's either going to go to positive infinity or negative infinity. How do we tell the difference? Well, this is a negative in front of here. That is that multiple, which means that this has been reflected. Been reflected over the x-axis, right? So it's been reflected over the x-axis, which means what? Well, if it's been reflected, it's no longer opening up. It's actually going to open down. So what happens is when we do this, it ends up opening down. So what does that tell us? It tells us the end behavior is that y heads towards negative infinity. In other words, it's going to be like this, not like this, okay? Because it's even degree, so it's either both up or both down, and because it's been reflected, right? So now we can draw this in. Past this 0 and past this 0, we know the thing's opening down. So this kind of gives us a start point. So at negative 3, it has multiplicity 2, so it comes up here and it bounces. Wing. And then at 0, it bounces again, because it's even degree, but it kind of bounces more abruptly, let's say. So, right? Then at 2, because it's multiplicity 1, it's going to cross through. At 4, it's multiplicity 2, so it's going to bounce. Now, you'll know you've done this right if at the final 0, is it supposed to cross through? Yes, yes, it is, because it's multiplicity 1. And then it links up. So that would be the sketch of that graph. All that from just the factored form and figuring out what the exponents are. Okay? And that is what multiplicity zeros can tell you about polynomials.